So we're looking at classification models, and this one we're looking at gradient boosting machines. Now in a previous video, we looked at decision trees, and so here's a visualization of a decision tree where it takes a number of questions, and this was a survey of our union members, asking them about priorities as we get ready for bargaining. And we were trying to classify whether they belong to the South location or not. So we created this binary classifier, and we were looking at variables like their satisfaction with their working location, their hours worked, whether the workplace felt safe, inclusive, so on, to create this decision tree. And the decision tree then started with one question. This question, I think, was about satisfaction with location. And then based on your response to that, if you were not satisfied, then it looked at your response to, I think this question here was about inclusivity. And so then what it would do is look at how your response to that question, and then it would go to a question here about workplace is safe, and that would put you into this subgroup that would make you to be at the South location or not at the South location. Now, the challenge with decision trees themselves is that every time you build a new decision tree, you run the algorithm on your test data, that you can come up with a very different algorithm. And that means your accuracy can change quite a bit every time you run a new tree. And so in the previous video, we looked at a method to address this called random forest. And random forest generates multiple decision trees. In fact, the default is 100 decision trees and averages their results together to improve the accuracy without overfitting the model. We're going to look at another alternative in this video, which is the gradient boosting machine. Gradient boosting machine, or GBM, tries to improve the accuracy in a single decision tree by starting with the single decision tree and then adding trees. So instead of averaging, this one adds. So the random forest averaged the trees, the gradient boosting adds the trees. And what we find out is, in terms of trying to gain accuracy, it outperforms the random forest model in terms of the speed versus accuracy. So one of the challenges with random forest is if we have a very large data set and we're building this decision tree and we redo it 100 times, it can take a while. It can be slow. So what we find is that if you have really large data sets, you don't want to do the random forest, but you want to improve the accuracy of the decision tree, use the gradient boosting machine. Okay, so the GBM classifier approach. Now, the challenge is that the GBM approach is more susceptible to uncorrelated predictor variables than the random forest. So in a random forest, it creates a decision tree based on, let's say it randomly picks 3 variables. It picks another decision tree and it's 3 different variables. It picks another decision, it creates another decision tree, and it's 2 of these and 1 of those. Because they're all averaged together, any variable that doesn't appear in very many decision trees gets weeded out. But in gradient boosting machine, because we're adding the trees, then variables that only appear in, say, 1 random decision tree continue to exist in the model. And so if you have variables in your system, in your model, that really are not highly related, right? We want to be careful about which variables we feed into the model. We want to do that exploratory data analysis, data visualizations, inferential statistics, make sure the variables we're choosing are related to that label we're trying to predict. If you throw into the list, because the benefit of decision trees and random forest and gradient boosting machine is it picks the variables, there's a tendency to just throw all the variables in and have it pick from that, right? It'll figure it out. I don't have to do any of that preliminary work, that exploratory data analysis. But if you're using the gradient boosting machine, it will push it to, it will influence it. Those unrelated predictor variables you threw in will appear in some of the random decision trees. And if you're using decision tree or if you're using gradient boosting machines, they'll continue to live there, which can give you some weird predictions and greatly influence your model. So that's why we do our homework beforehand and do our exploratory data analysis to make sure the variables we're including are relevant, being mindful that if they're not, it will impact the model, because even though it's picking from the variables, how it randomly selects the test, the train, what order it puts them in might lead it down one random rabbit hole. The other thing to recognize is that the GBM and the random forest are highly impacted by poor predictor variables, by uncorrelated predictor variables. GBM more so, right, because of the adding, but still all of them are going to be impacted by if you throw variables in that aren't related. All right, so let's go and look at how to do gradient boosting machines. Information about tuning hyperparameters and identifying important features we'll do in our next video clip. So we'll talk about how to improve our decision trees, our random forest, and our gradient boosting machine in our next video. But right now, let's look at just introducing our gradient boosting machine. And so just a reminder for the 50 millionth time, you can find this Python workbook at drstephpowers.github.io/BIA. We are working on classification, so click on this one. And then once you are into GitHub, you will need the relevant Excel files, put them in your Google Drive, open this in Google Colab, save a copy so you can edit it, and make sure you link it to your files within your Google Drive so that you have access to all of this. All right, let's go in. We're towards the end of the document if you haven't been going through all the videos with us. We're in the section called GBM. Now we can use GBM for binary labels, south, no south, and we can use it for our multi-labels like north, south, east. So let's do this. We are going to do it for binary labels first, which means we can calculate a confusion matrix, precision score, recall score. So we've included those. For all classification models, we can do accuracy scores because we have the true labels. And we're going to have it tell us the train and test. It's going to then take our data set and separate it into train and test rather than us specifying specific data. And in this case, gradient boosting machines, we're going to use gradient boosting classifier from sklearn.ensemble. So import. In our previous videos, we added, just make sure it's still there, df2.head. We added the variable south so we could have this binary classifier. If you're just joining this video and didn't do the previous, or just open this file after taking a break from the previous, make sure you go back and create this variable south. Scroll up through this workbook to find that, where we add this variable south and we label it 1 if it's south and 0 if it's everything else. So once we've done that, we can then separate the test and train. Doing our train test split, we're going to use question 2, which is part-time, full-time, 13, 14, 15, 18, and 20. These are our Likert scale ordinal questions about, are you satisfied with the amount of hours worked, the time of day, the location where you work? Are you, do you agree that the workplace is safe? Do you agree that the workplace is inclusive? All right, and then we're going to use that new variable south as the one labels we're trying to predict. We're using our 80-20 rule, so we're going to test 20, train 80, and we're stratifying over south to make sure that both the test and the train data have south and no south in them. So we'll load that up, and in fact, I'm going to actually run this. Let's do random state equals, and what was the number we were using, 1800? 1900? Probably 1900. I should just use the same number. Random state always 1900. All right, got to pick my favorite number, I guess, and just make it that. All right, so we'll do 1900. And that just allows us then to compare, because it'll be the same train test split as in the previous scenario when we looked at it for the random forest and the decision tree. Okay, don't forget a comma after that. If you don't do random state, then it will just randomly generate your test and train. You'll get a different accuracy and model every time you do it, which totally can do that and see what it looks like. All right, same process as all classification models. Call the classification model, gradient boosting classifier, give it a name, we'll call it GBM. We'll fit our GBM with our X and Y training data. We will predict with our GBM model on the testing data for X, and it'll give us the predictors for Y. When we do that, we can see that it gives us 4 possible individuals it thinks is from the South location. We can then test the accuracy underscore score, Y test, Y predict, and it gives us this accuracy here, 61.5. If we go back, let's go back in time to the other Souths. Here's the random forest accuracy, 1900, 69% for the random forest one. Let's keep going back in time to the single decision tree. Find it in here somewhere. South, 1900, 69%. So decision tree and random forest here had a 69% accuracy, and we can see here with our gradient boosting machine, way too much stuff in this thing, that this one was at 61.5%. Okay, so when that happens, if the gradient boosting machine has a lower accuracy, we have to ask ourselves if it's being impacted by unrelated variables, right? Because it's going to add to the model another tree, and if that tree has a random different variable in it, then it's going to influence this. So it's quite possible that this one has a less accuracy than the random forest. Random forest is great if we have a small data set, gradient boosting machine if we have a big data set, and this one's not particularly big. Because we have a binary label, we can do a confusion matrix, and we can plot it. And you'll notice why it's worse is because it went from having 1 false positive to 2 false positives. So we can see that change here. It seems there's still 3 false negatives in our prediction. So our precision score here is 50%. Our recall score here is 40%. So this model is not working as well with our data set as some of the other models. All right, here's your chance. Create a gradient boosting machine, a classification model. This time not with the binary classification, but with the multi-label. So we're going to use question 23, north, south, east. But same predictor variables. Question 2, 13, 14, 15, 18, and 20. So pause the video and see if you can't create this classification model. So first thing we always do is put in the packages that we need. Always good practice, even though technically you just loaded them all. We don't need precision, recall, or confusion because we have multi-labels here. We're using the gradient boosting classifier. We're going to have it decide what is test and train. We want to use the accuracy score to see how good of a model it is. Then we're going to load our data. Or separate our data, I should say. Not loading it into the model yet. And we are going to be predicting question 23. Test size still 20%. If we're comparing it to the decision tree and the random forest, I think I used the random state of 200. So let's do that so that we can compare them. All right, so we train and test. We got our separated data. Now we're going to call the model, fit the model, and predict the values. Okay. So we are going to call gradient boosting classifier. We'll call it GBM. We will fit it with our X and Y training data. We will predict using our X test. We get our Y predictor values. Notice here it is predicting 1, 2s, and 3s because it is 3 possible labels. And then we want to test the accuracy. And so this particular one, the accuracy is 46%. Let's do a comparator as I scroll back in time. And so this one here was the random forest. The random forest had an accuracy of 61.5%. So random forest did much better there. And if we go back even further in time to our single decision tree, make sure that's the right one here. So question 23, when we did it here in the super complicated model, it was at 54%. When we simplified it, it was at 61.5%. So you can see how this gradient boosting, oh, I've gone too far. Too far, and go back in time. Sorry, next video. All right, so we had 46% in this particular model. So using our gradient boosting machine to now work as well in this, that's because there's a lot of variables that we've included here that really don't tell us anything about the location. What we'd want to do to improve this model, to get that accuracy higher, is do more exploration first and look at those different ordinal questions, the nominal questions. Maybe there's other ones we didn't include besides 13, 14, 15, 18, 20, and 2 that are better predictors of the south location. And if we can clearly see that question 13, for example, has nothing to do with the south location, everyone seems to feel the same. When we do our inferential statistics, when we do our data visualization, then we shouldn't include it as even an option because it's leading some of the decision trees on a tangent in the wrong direction. And so we can clean this up and make it tighter, make it more accurate by doing our homework first to make sure the variables that we have chosen are the most relevant. And then, of course, it comes down to how big our data set is. There are other methods for improving our model, which we're going to look at in our next video.